This is the pure resistive circuit, which consists of the alternating supply voltage, and that is connected with this resistor through this conductor. Okay, so due to the potential difference inside here in the alternating supply voltage, the electric field will develop inside this conductor. Okay, and inside this conductor we have the free electrons, and due to that electric field from the alternating voltage, the force F will be exerted on each and every electron present inside this conductor. Okay, so due to which that electrons will start motion. Okay, and the motion of that electron is called the current. Okay, so due to this supply alternating voltage, the current I will be developed inside this conductor. Let's deeply understand the behavior of electron inside this conductor. So for that, let's consider this side as a positive for a while, and this is a negative. Okay, so here the electron will the force F will be exerted on the electron inside this conductor, and let's say we have the electron inside this conductor, and due to this polarity, the force F will be exerted on this electron, and it will start motion in this direction. Okay, so here we know that this supply alternating voltage is changing its polarity, and now the polarity is changed, and this side become negative and this become positive. Again, that same electron is moving will move from this mean position toward this side. Okay, and here again this polarity will be changed. Okay, and this side become positive and this become negative, due to which this electron will again start motion towards this right side of this equilibrium position. Okay, so here in our country, the frequency of the alternating voltage is 50 hertz. It means that here this electron inside this conductor will also vibrate 50 times in a second about their mean position. So here, just like this electron which is vibrating about their mean position due to change its polarity. Okay, so here this vibration is more like the simple pendulum. In simple pendulum we have the mean position and we have the extreme position. So here we also have the mean position and the extreme positions. Okay, so let's say here this electron is in motion, we call that as a current, and when that here in the mean position, the magnitude of this current is 0. Okay, and that is increasing and will reach here to the maximum value. Okay, so again when the polarity is changed, okay, that electron will again start motion in the opposite direction. Okay, and that will be decreasing and become 0 here. Okay, so at this position that electron is in motion due to the inertia of the electron, and due to the inertia of the electron and the change in the polarity of the alternating voltage at the instantaneous time. Due to these two reasons, the electron still will be in motion here in the opposite direction. Okay, so in this way it will reach here to the maximum position. Okay, so here the magnitude will be maximum but in opposite direction. Okay, so here I am going to label that when the electron is in mean position, their magnitude is 0, their direction is also there is no direction, but here when it reached to the maximum, the extreme position, so in the extreme position the current will be the maximum, the magnitude of the current here, okay, will be the maximum, and here we have in this extreme position the current is called Im, which is the maximum. Okay, So now we have to go for the mathematical interpretation, and we know the supply voltage is given by the formula which is equal to Vm and sine omega t, and let's call this as equation 1. Okay, so that supply voltage is responsible for the current here, and that alternating current will pass through this resistor here. So now divide this equation 1 by R here. Okay, so this equation 1, V by R is equal to Vm by R and into sine omega t. Okay, so we divide that R on both sides. Okay, so their net effect is 0 here. So let's say this is equation 2. Okay, now we know from the Ohm law, and which is so here the Ohm law is applicable. So we have the voltage, we have the current, we have the resistor. Okay, so according to the Ohm law, V is equal to IR, and from this I is equal to V by R. Okay, so here instead of this V by R, we will put this I, and that equation to become I, okay, is equal to, now this is Vm by R. Okay, so Vm is given by I, Vm by R is given by Im. Okay, and which is equal to and the rest one is the sine omega t. Okay, so here we have that sinusoidal equation for this current. As I have discussed, this current is in motion, it is vibrating. Okay, so this is the amplitude of that current, as I had mentioned here. This is the extreme position, and this extreme position is we called as a maximum amplitude, the peak value here. Okay, so this is I am also the peak value here. Okay, and this is the instantaneous current, mean that the current at each and every instant here. So if this electron is moving in this direction, okay, in the half cycle, the half let's say the positive half cycle, so their magnitude is changing at each instant here. Okay, so at the each instant the magnitude of the current is given by the instantaneous current, and which is called the I here. Okay, so the relation for that instantaneous current is given by I is equal to Im sine omega t. Okay, so at some time, specific time, and the angular velocity of the electron here in the in this case. Okay, so why this angular velocity? So you may think here is that this electron is actually moving, the motion of this electron is translational. Okay, so why we put here the omega? So so the answer for that is this, here this electron is vibrating. Okay, and we know we can draw the vibration of the electron in the Phasor diagram. So in the Phasor diagram we have the vector, and that is moving in the anti-clockwise direction. Okay, so when it moves in the anti-clockwise direction, their motion is actually the angular velocity. Okay, so their motion is actually a rotational motion, and their velocity is called angular velocity, and each and every instant the value of that current, that instantaneous current in the Phasor diagram is given by I is equal to Im sine omega t. Okay, so now we have two equation. One is this 3, and the other one is this V. So this 3 and the other one is this one equation. So if we compare this equation 1 and equation 2 here, okay, these both, the equation 1 is actually the supply alternating voltage, which is the function of the, which is a sine function, and similarly we have the current, the alternating current, that is also the sine function. Okay, so from here we conclude that this voltage and this current both are the sine function, so both are in same phase. Okay, so we have the diagram here. Okay, in this diagram, this is actually the sine wave or the sine function for the voltage, alternating voltage. Okay, so this is for the voltage, and here this is the maximum, the peak value of this voltage. Okay, this is the peak value, the maximum amplitude, and here it starts from this 0, and this is the sine function. Okay, and we have the current, and that current is also the sine function, so it also start from this position, and this will be the sine function. Okay, so both are the sine function. Okay, and therefore there is no change in the phase difference. Okay, now this sort of diagram can be represented by the phasor. So this is actually the phasor diagram of the AC through resistor. We have that same sine function of the voltage, which is given by this upper one, and this lower one is the sine function of the current. Okay, and so we have there two graphs. So the phasor for that is this. So as we know that in the phasor diagram, we will have to consider the magnitude of this vector is equal to the peak value of that sine function. So here this is the magnitude of the current, so this is the vector for the current, and the magnitude of this vector is equal to the maximum amplitude. So here this is the maximum amplitude, and its magnitude is equal to this one. Okay, and now the magnitude of the maximum, the peak value of the voltage is more than this current. Okay, so therefore we draw the here we draw the vector with the larger magnitude here. Okay, so that vector will represent the sine wave for the alternating voltage. Okay, so this small one will give us the alternating current, and this larger one will give us the alternating voltage. So here these two phases, these two vectors are in they are in motion, they are in phase to each other, so both are moving in the same distance. So here if in this position both the voltage and current are 0, so at the 0 position here these both are the 0. Okay, now both reach here at 90, so the maximum value of this current will be this, and the maximum, so this is actually the 90. Okay, so at this 90 we have the maximum value of the voltage, and which is given by this projection, and the maximum value of the current, which is given by this projection here. Okay, now again it will reach here. Okay, so this is the maximum value of voltage that becomes 0 at 180 degrees. So this is actually 180 degree. At 180 degrees the voltage is 0, and similarly the current is also 0 here in 180, so therefore both are 0 here. Okay, now at 270, okay, at 270 these two vectors will be here in. Okay, and this is the phasor for the alternating voltage, and their projection is here is this, and it will give us the maximum value in the opposite direction. And here we have that same the phasor for the current, which the less magnitude, and their projection is given by this. Okay, so this is the phasor diagram for the alternating current and voltage through a resistor. Okay, now we are going towards the power. for the power, we know the relation for the power which is given by this P is equal to I instantaneous and voltage instantaneous here. Okay, so we'll have to put the value of this instantaneous current and this instantaneous voltage from the equation 3 and equation 1. So due to that the power here, instead of this I will put Im sine omega t, and instead of this we will put Vm sine omega t here. Okay, so this become Im Vm, okay, and this sine omega t and this sine omega t will become sine square omega t. Okay, this is actually that power. Okay, so let's call this as what we can say equation 4, and here the sine omega t is actually give us the value from the 0 to 1. Okay, from 0 to 1, and here if this becomes sine square, so this becomes 0 square 1 square. Okay, and the average of this sine square is given by this 2. So these are the two values, so we'll divide that by 2, it will become equal to 1 over 2. So here instead of this sine square omega t we will put 1 over 2, due to which that equation 4 become this. So P is equal to Im Vm, and instead of this sine omega t I will put 1 over 2 here. Okay, so we know that 1 over 2, so instead of this 2 which is equal to we can put this 2 power 1 over 2 multiply 2 power 1 over 2. It means that square root of 2 and square root of 2, instead of this 2 we will put that. So this equation 5 become this. So equation 5 is equal to P is equal to Im Vm divided by square root of 2 and square root of 2 here. Okay, so here Im divided by square root of 2 is the RMS value of the current. Vm divided by square root of 2 is the RMS value of the current. So therefore we can write the power is equal to I RMS, and similarly we have the V RMS for V by R square root of 2, which is equal to V RMS. Okay, so this is the expression for the power here. Okay, in this power diagram, let's break this power diagram to each quarter here. Okay, so this is the 90 degree, this is the 180 degree. Okay, so I am going to put to break this. So this is actually the 90, this is the 180 degree, the second quadrant, and this is the third quadrant, this is the fourth quadrant. Okay, so this is actually the first quadrant, this is the first quadrant, this is the second quadrant, so this is the second quadrant, third quadrant, and this is the fourth quadrant. Okay, after fourth quadrant one cycle will be complete. So here this is actually the voltage, the sinusoidal wave for the voltage, and this is the sine function for the current. Okay, so we know that P is equal to IR. Okay, so here P is equal to IR. So for this first quadrant, P is equal to IR, and I am going to put here is that. So for this first quadrant, P is equal to I and V. Okay, So here in this first quadrant, the value of the I is positive, and also the value of the V is positive, okay, and it will give us the positive value. So here the value of this power is positive. And similarly, here in the second quadrant, the value of second quadrant, the value of the current is positive, and the value of the voltage is also positive, so it will also give us the positive value. So for the third quadrant, okay, for the third quadrant, the P is equal to IV, and the value of the current is negative here, okay. So this is actually the value of the current, and this is actually the value of the voltage. Both are negative, so this is negative and the other one is negative. It again gives us the positive value. So here this graph of the power is positive, okay, so it is increasing. So here the amplitude of this power is increasing, because both this is actually the multiplication of this voltage and current, both are multiplying. So for the fourth quadrant, the power is given by P. This I is negative here, okay, and the V is also negative, and it is equal to positive. So here the power will be positive at each and every position. So it means that the power will always deliver from the source towards the resistor, okay. And this was the in-depth intuition of the AC through resistor. So the one thing is remaining here. We draw this sinusoidal function for the current with the less amplitude, with the less maximum value, and we draw that for the voltage with the maximum amplitude. So with the higher amplitude, and here the amplitude is less. So the reason behind that is this: according to the Ohm law, V is equal to IR. So here this V is more than this I, because this V is equal to I with multiplication of this resistor. So this resistor will have some value, okay, this resistor will have some value, and if we multiply that resistor value with the current, then it will be equal to this voltage. So this voltage is more than this current, so therefore we put the maximum value for this voltage more, the amplitude of that is more here, okay, and the amplitude or the maximum amplitude for the current is less here. This is because of this reason here, okay. So here this voltage is more than this current, okay. So if we multiply the resistance with the current, then it will be equal to the voltage. So therefore we put the maximum value of the voltage with the higher amplitude, and the maximum value of this voltage with the lower as compared to the amplitude of that voltage.